Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about the number e and the function e to the x. It's chapter 5.4 for pre-calculus. All right, so before we get into that, let's talk about the compound growth model. This is an extension of our growth model. We're adding a couple parameters to compounded growth. So a is still the ending amount, p is the initial amount of the principal, then 1 plus, remember we need to retain the 1 to retain the principal, plus r over n, where r is a percent increase as a decimal. N is the number of periods for a given t, which is normally in years, and then t is typically the number of years. All right, so we're going to go straight away into a problem for you. You've walked into a Wells Fargo bank and you have $3,000 and you are offered 4 different choices. One is to take that $3,000 and invest it for 5 years at 4.9% compounded daily. And by the way, these figures you probably haven't seen for about 20 to 30 years, and you won't see them now because the interest rates are below 1%. But let's just say that things have changed now, and you can get 4.9% compounded daily, 4.9% compounded monthly, 4.95% compounded quarterly, and 5% compounded yearly. And your job is to figure out, using the formula that I just gave to you, which is the best offer. So I'm going to pause here and then we'll go through the numbers. All right, so these are the values that you should have come up with. $3,832.80 for daily, $3,830.95 for monthly, $3,836.63 compounded quarterly, and that ends up being your best choice. So in this case, let's go back to the figure and talk about what we put in for each value. All right, so principal is going to be $3,000. 1 plus, in the case of the daily, is 4.9%. So the rate percent increase is a decimal 0.049. N is going to be the number of periods for the given t or years. So a daily would be 365. So it'd be 0.049 divided by 365 plus 1, and then taken to the 365 times 5, which is a period of years, number of years that we decided that we're going to invest the money to. If it was quarterly, then n ends up being 4. I believe the quarterly rate was 4.95%, so 0.0495 plus 1 taken to that value and then multiplied by p. So remember your order of operations. You're going to evaluate what's in parentheses, take that to the power, then multiply it by p, and that will get you your ending amount. All right, so now let's talk about a gentleman by the name of Leonardo Euler, who is a Swiss-German mathematician in the 18th century. And he was just kind of doodling around with some numbers, and he asked himself, okay, what happens if we take 1 plus 1 over the n to the power of n as n goes to infinity? And he was able to work out that the value is approximately 2.718. And he applied that value as the value of e. So e is a number. It actually is an irrational number, which means the values never repeat and the decimal values never end. So e, like pi, is an irrational number. E is a number that's approximately 2.718. That value is worked out by Leonardo Euler in the 18th century. And we're going to use that to consider our compounded growth rate. But now we're going to talk about what happens when that rate is compounded instantaneously. And we're going to use e to figure that out. So let's review this again. E is defined as natural base. It's derived from an expression 1 plus 1 over the n to the n as n approaches infinity. It's an irrational number and is equivalent approximately to 2.718. And I think part of the confusion comes in with students when they don't realize that e is just a value that's approximately 2.718. And they think of it as something else like a variable just because it's a letter. So please be careful. E is a number. It's an irrational number. And again, approximately 2.718. Right, so again, furthering our discussion about E, natural base exponential function form is y is equal to a times e to the RT, where again E is 2.718, R is a value greater than 0, a is greater than 0, and we have an exponential growth function. Where we have R less than 0, which means a negative exponent applied to E, then we end up with a fraction, so to speak, or a value between 0 and 1 for our B, or our base, and then we end up with an exponential decay function. Right, so what I want you to do, and we'll get back to our instantaneously compounded growth model. What I want you to do is I want you to fill out these values for the function y is equal to e to the negative 2x and y is equal to e to the 2x, from x being equal to negative 4 through 6. And remember, e is equal approximately 2.718. You should have a function for e in your calculator to evaluate this. So I'm going to take a moment to pause here, and then we're going to come back and take a look at your numbers. All right, moving on. These are the approximate numbers you should get as you see as the values are increasing from x, negative 4 to 6. In the first function, y is equal to e to the negative 2x. You can see the values go from approximately 3,000 down to very close to 0. And for the function y is equal to e to the 2x, the values go from close to 0 to very large numbers. Again, 3,000 at 4, and then 22,000 plus at 5, and so on and so forth. So with our function, just because the base is e doesn't mean it has to be exponential growth or decay. You can see when the exponent applied is a negative exponent to e, the function is a decay function, and when it's a positive value, it's a growth function. So let's take a look at e to the 2x graphically. These are approximations. So e to the 2x is in red here, and e to the negative 2x is in blue. So we're going to ask ourselves, what is the domain? And by the way, when the value of x is equal to 0, e to the 0 is going to be 1. E to the 0 here is 1, and this is where the two graphs cross each other. So what's the domain and what's the range of each function? Well, domain is going to be all real numbers because we can supply any value for x and still get a real number result for y for both functions. And the range is going to be y is greater than 0, as you saw in this function. As x gets bigger and bigger, the value of y became smaller and smaller, but never got to 0. So y is greater than but not equal to 0 is the range. And similarly here, the exponential growth function y is equal to e to the 2x. As x gets closer and closer to negative infinity, y gets closer and closer to 0. And as x goes to positive infinity, then y goes to positive infinity. Right, so let's move on and let's talk about our continuously compounded growth model. So remember, going back to E for Euler, remember 1 plus 1 over n as n goes to infinity to the nth power is E. So we're going to substitute E to the RT here for this function, which includes Euler's analysis. And we end up with a formula for continuously compounded interest as A ending balance is equal to P, the principal, times E to the RT, where E, again, is just E 2.718, R is the interest rate, and T is the number of years. All right, so we're going to go back into Wells Fargo, and now the question is they forgot to let us know that they also had an option 4.85% compounded continuously. And now we're going to evaluate whether or not option number 5 is better than option number 3. And so I'm going to take a moment while you do that. So remember, A is equal to P principal 3,000 times E to the R, expressed as a percent decimal, 0.0485, taken to the multiplied by T and taken to that power. So P times E to the power of 0.0485 times T, which is 5 in this case, and I'll allow you a moment to evaluate that, and we'll come back. All right, so 3,000 times E times 0.0485 times 5. And, moving on. You should come up with a value of $3,823.29, which is less than your preferred option number 3. So we're going to stick with a quarterly interest rate of 0.0495%. All right, some classwork for you to do. What is the value of $4,000 after 4 years if it's compounded continuously, quarterly, and yearly at a rate of 6%? I'm going to pause here while you figure that out. All right, so continuously you end up with $5,085. Quarterly, 4,000 times, again, 1 plus the rate, 0.06, divided by the number of periods, 4 to the power of 4, number of periods, times the number of years, 4, so to the power of 16, $5,075.94. Yearly, just straight away, 4,000 times 1 plus 0.06 divided by 1 to the power of 4 times 1, $5,049.91. And you can see that the continuously obviously brings you the same interest rate as all the others, will bring you a greater return on your money after 4 years at the same interest rate. All right, so let's do a little bit more work here, and then we'll call it a day. What's the value of $3,000 to the nearest penny after 3 years if it's compounded continuously, quarterly, yearly? And then we're going to use 2.718 as a value for E. If you don't already have it in your calculator, I'll come back. We'll take a look at the answer here. Nope. I believe I don't have the answer for you. So you're going to have to figure that one out yourself. And that will be, let's take a couple more problems here. All right, so you can do the same problem for $3,000 invested 3 years continuously, quarterly, and yearly at a rate of 5%. And take a look at these numbers if you want some more work. And then lastly, here's a question for you. You have an opportunity of purchasing Call of Duty Advanced Warfare for $60 and a new Xbox One for $350, or keeping the money for later use when you retire at the age of 68, which is going to be, we'll just say you're 18 now, 50 years later. What's the future cost of purchasing Call of Duty Xbox One, assuming that you're growing your money at a rate of 8%? We're not considering inflation. So we're going to take our $60 and our $350, which we would have spent, and we're going to invest it at 8% for 50 years. So 410 times 1 plus 0.08 to the 50th. And let's see if I've worked out a value, and it looks like I have not. So you're going to have to figure that out on your own, because I'm running to a conclusion on my time. And then I'll give you another problem. I may or may not have the answer to that as well. No, I don't know. We'll see if I can actually work that out in the time that I have left. You're 23 now. You have a fancy job, and you want to figure out whether or not you will buy a used Honda Accord at $15,000 or a new Mercedes at $45,000, and you want to figure out the future cost again if you invest that money for, now we're saying it's 45 years at 8%. So you can figure that out, and in the minute that I have, let's see if I can figure it out and come up with an answer for you. Okay, so I've worked out the answers for you. And so if you choose, after 45 years, if you choose to, now I guess we're assuming that you're 23. Oh yeah, it says you're 23. All right, so we're assuming that you invest your money wisely and you buy that new Honda Accord. You can either have 2 hunks of metal or 1 hunk of metal and no money, or you can have your hunk of metal Honda Accord and you can have $957,000 in the bank. So you should choose wisely. And I guess the point here is that this curve is, the exponential growth curve is working for you in your favor, right? If you're young, especially if you're young, because this value here, this exponent is very large. And when you're dealing with very large initial investments as P, then you're going to end up with some pretty large numbers. So the Xbox choice is 50 years later is worth about $19,000 to you. All right, so that's it for number E and the function E. Join us